Welcome to the PTA Real Estate Podcast. I'm your host, John Caligiuri. I'm accompanied by my co-host, Nick Kelling. Nick, how you doing
Howdy.
tonight? We have
Great.
a very special guest today, Caleb Nolen. I've known him for a long time. Played lacrosse with him. Caleb, take it away.
So my name's Caleb Nolen. Currently I'm a cutting tool design engineer for a company called GWS Tool Group in Menominee Falls, Wisconsin. Previously, I was a hydraulic systems design engineer and a electric motor research and development engineering intern for about a year at a company called Montevideo Technology Inc. So most of my work experience is just development engineering and research. So right now, what I do, we make basically just carbide round tools. So we supply a lot of auto manufacturers, people in the defense industry with their precision hole drilling equipment. We make a lot more than that, but that's all I do.
Yes, for all of our listeners, we have a very veteran base podcast. So for all you veterans out there and knuckle draggers, bring out your notepad and pen. You're going to learn a lot. Just for our background, I've known Caleb since high school. He was on my lacrosse team with me. I would say he's a very good friend of mine, great teammate. I'm very excited to have him on the podcast. He does own, or I would like to get into the backbones of it, a 3D printing business. I know we can't go into the details because there's still floating patents. Not a big deal now with mentioning this guy's patents on the horizon. So, Caleb, can you give us your background of how did you get into mechanical engineering and kind of go from there?
Yeah. So I kind of always knew that I wanted to be an engineer of some kind. Like from the time I was in kindergarten, I was like trying to build stuff out of cardboard boxes and stuff instead of watch TV or play video games. So that kind of led me down the path of just trying to build a bunch of different stuff. I figured out I was a lot better at doing stuff with my hands than I was at programming, although I picked that up later in life. But when I made the actual decision to go to MSOE, I had known since like sixth grade I wanted to do mechanical because I just liked cars, which seems to be the answer that most mechanical engineers give, or a lot of them anyway. But I didn't really know exactly what it would be going to school for mechanical engineering. It's a lot different than what you would expect. Most design engineers are either an electrical or a mechanical engineer, and they don't teach you really anything about design at school. So they really just teach you how to do, like, you can do calculus when you come out. They teach you how to do a little bit of programming, kind of like fundamental stuff. But what they don't teach you about is like the mindset of approaching a problem that does not yet have a solution. They teach you how to solve all these problems that are confined to these boxes, like a word problem on a math test, stuff like that. Or they can do that with engineering principles as well, where they break it down to the point where you know exactly what variables you're dealing with, where in the real world you don't. So what drove me to become a mechanical engineer is that I just love trying to find answers to questions that don't have them yet. And that seemed to be the best place for me to go. Although I'll add a caveat, I probably retrospectively would be a software engineer instead of a mechanical because they get paid like way, way, way more.
For the layperson, which I am, what problems do a mechanical engineer solve or set out to solve? Because I still have no idea.
So mechanical engineers, it's kind of a weird field inside of engineering because it's so broad. I graduated, or I actually didn't graduate. That's probably something we should talk about too. But some of the guys in my class, like I have people who are on my lacrosse team because I played D3 lacrosse at MSOE, Milwaukee School of Engineering. But some of my teammates, they work over at Milwaukee Tool. One of them works with me at GWS. One of them works at a company that builds like pontoon boats. So to answer your question, mechanical engineers are kind of just tasked with solving any problem that there isn't a specialized field for at your company. So like what I end up doing a lot of the time is you're doing manufacturing stuff. You're figuring out why the assemblies you're trying to build aren't going together properly. You try to figure out how to increase your product performance. It can be a pretty broad range of stuff. I specifically specialize in research and design. So
you do research and design. So let's just take the pontoon boat as an example. So for all the people out there who don't know what a pontoon boat is It's the middle class dream. It's basically just it's made for inland lakes. So say you're a mechanical engineer at boat A company and there's something wrong with the motor, they come up to you and say, "Hey, this motor is shorting out at this nautical knots, figure it out."
So that's actually going to be more of a lab technician is going to be trying to troubleshoot that.
So give me an
Um,
example of a problem that you would solve.
so a problem that you would solve would be in the pontoon boat scenario. Let's say my friend Matt, he does mechanical engineering as well. His system is mechatronics, so he does everything involved with. It's a little bit of electrical, but it's all the electric motors that are moving the different parts around on the boat. And so what they'll do is they'll give them like, you get this supply voltage, this supply current. You need to be able to run this number of motors for this amount of time without draining the battery. And then he has to go out. He has to figure out what motors do I need to pick. What are their power? Like, what's their power draw? How much weight can they move? How do I design the assemblies, or how do I communicate with my other team members who are designing like the linkage mechanisms and everything like that, so that the linkages will move with the amount of power that the motors can provide. So you're really working a lot of the time just from like somebody else comes up to you and says, I want something that does this, but they don't know how to make it. So they just say, I want the motor to drop down when I press a button. And that's all they're going to tell you. And they're going to say, and by the way, you get 12 volts and 2 amps to do that. So then you just go figure out, using your previous knowledge and the parts that you have available, how you're going to solve that issue.
So basically, you're the Q. To do a James Bond reference, you're the Q of your company.
Yeah, kind of.
If I came to you and I said I need a parachute with a Tommy gun and I need a hot blonde, you could figure it out. Maybe not the hot
Yeah,
blonde.
I'd figure out. Well, I'm already a hot blonde, so I'll get you the Tommy gun. But
That's awesome. So you went to school for it. Why didn't you graduate? Was it COVID, or did you realize it was just dumb to go to school? And has it hindered you?
Sorry, what was that last question?
So you not graduating, has that hindered you in your career field? Because I know if you're Joe Schmo going to school for your business administration and you do not graduate, that definitely would hinder you. Has it hindered you in your career thus far?
I don't think that it's hindered me. What I find is that when I'm interviewing with people, I always tell them up front that I did not graduate. And typically they ask me why. They don't say, oh, we're not interested. And the answer to the previous question that you asked about why I didn't graduate, it was a little bit of COVID. And then also I realized that I had actually been getting hit up by recruiters on LinkedIn for full-time engineering jobs. And while I was in school, because I thought that I had graduated because of the amount of work experience that I had posted on my LinkedIn. So I just decided that I actually dropped out because I was doing way too much. I was on the lacrosse team. I was on the first and second cohort of student fellows for the Create Institute, which is like supposed to be implementing like hands-on learning experiences for students in their classrooms, which I think is super important for engineers. And then I was also working at the Fluid Power Institute so I could pay for like my rent and food. And on top of that, I was also starting the 3D printer company that we talked about. So I was just stretched far too thin. I also was part of, it was a regional version of the National Science Foundation's program called I-Core, where they teach you how to transition deep technology into a consumer technology. So I was just like doing way too much.
Okay, Caleb, you can't just say things like deep technology to consumer technology without elaborating.
Okay. A deep technology is a lab technology. So it's something that's been developed and works. For example, you could think of something like 10 years ago, they were able to create the reactions that are currently being used in supercomputers in a lab environment, but not in a computer. So the deep technology is something where you know it works. You can create this output every time you do this little experiment, but you have yet to turn that little experiment into something that consumers want to buy. And that the thing that consumers want to buy is the consumer technology.
Okay. So basically taking a supercomputer and turning it into an iPhone is basically or a 1980. Is that too broad of an example, or
It's like taking a bunch of particles out of thin air and then turning them into a computer. That is what supercomputing is, and that was what the transition between deep technology and consumer technology was. Although technically, maybe quantum computing is still in the deep technology phase because it's not widely adopted. But
okay, this because the particles into a computer was a little above my pay grade. Can you give us an example just so people can understand it a little bit better?
Yeah, let me think. Something that's easier to understand. A deep technology, at the time that we were in the program, 3D printing was still considered kind of a deep technology where consumers really haven't figured out a way to utilize 3D printing super well yet. It's just kind of making like action figures and that kind of stuff. And what we were able to, I mean, they do use it I used it when we were building precision electric motors. We do a lot of fixturing and measuring equipment with it, or prototype fitment things. But there's not really a widespread consumer application for 3D printing yet. So that's actually what we were working on in the program, was taking available 3D printing technology and turning it into something that could manufacture parts that consumers would want to buy straight off the printer instead of just little knickknacks that really have no meaning.
So yeah, elaborate more on your 3D printing business. Kind of give us why you thought of it, like why you started it, who you started with, and kind of start from point A to point B. And I know you have some patents on the pipeline, so be as broad as you want, be specific as you want. I want to follow the journey with you.
So it started off several years ago. I was a sophomore in college, so that was 2019. I came up with an idea for how you could control a 3-axis system. So 3 axes, like you imagine in your math class, you have like the X and the Y plot, and you got to do like plot a parabola on it or something like that. You imagine that, but add a 3rd axis, that's the Z axis. You got X, Y, Z. And you can automate that with electric motors. So you could take a slide and make it move on the X, Y, and Z axes. I figured out a way to control a X, Y, and Z axis system with Microsoft Excel using VBA. And I was like, oh, I could make a 3D printer with this. I don't know what I would do. But then as I was messing around with it, I realized that I could make the printer go a lot faster using my VBA application than I could get the printer to go using the stock firmware. So that's when I decided that I wanted to try to build just a fast 3D printer. And that's really all it started out as, is I knew I could build a fast 3D printer, but I didn't know what I was going to use it for.
So you said you wanted to build a fast 3D printer. What is the industry standards that a 3D printer is? And then if you can tell us, what can your 3D printer do? Give us the
the 0 to 60.
Yeah.
That's a super broad question. I'm going to break it down into smaller pieces. There's a lot of different kinds of 3D printers. So the type of printer that we are building is called an FDM, which is called a filament deposition machine.
Before you go in the breakdown, how you said that's a really broad question. Let me break it down for you in small sections. Is the most humblest brag your retarded thing?
That's not what I was trying to say. I lost my train of thought now.
Good.
What was I talking about? Yeah, good. No, FDM, that's what it was. So FDM, most consumer printers are FDM machines as well. They use something called filament. So there's an extra process involved with that, where you take a bunch of plastic pellets and you injection mold them into a long string. And that long string gets fed into the extruder on the 3D printer, which is just a motor that's pressing that piece of plastic line into a really hot nozzle, and that nozzle melts the plastic, and then it comes out of the nozzle and goes down onto the 3D printer bed. What we are doing is we're removing part of that, and this is not something that's novel, but we built a extrusion screw extruder. So instead of having a filament, like a long plastic line that feeds into the extruder, we just dump pellets in. So it makes the material cheaper, and it also makes the printer faster because I don't have to mess around with jammed filament, and I can change the output size, like the nozzle size, very easily, where you wouldn't be able to do that with a filament printer. So that is where all of our supporting technology that we did come up with is based on trying to facilitate doing extrusion screw 3D printing in the fastest way possible. So it's a lot of stuff dealing with
what is supporting technology and what is an extrusion screw?
Okay. A supporting technology is something that exists in order to make a different technology more efficient.
Okay.
And an extrusion screw is imagine like a hardware, like a decking screw you get at the hardware store. So when you look at that screw from the side, it tapers to a point at the bottom. Imagine instead of it tapering to a point at the bottom, it tapered out, and it was a longer taper, kind of like that. So sorry, I realize some people probably can't see me, but it's basically a cone but it still has the threads on it. So as the screw spins, the plastic pellets are forced down the threads, and because the body of the screw is getting larger, it forces those plastic pellets to rub against the barrel, the outside that the screw is stuck inside of a metal barrel, and as those plastic pellets create friction between the screw and the barrel wall, it actually melts the plastic. So you're going to get like 20% of your heat from band heaters that are just like little plastic or little metal heaters that you strap on the outside of the barrel. That's just for the heat continuity across the barrel. But then the actual heat that melts the plastic is from friction inside because it's all being forced out the nozzle.
Okay, that somewhat makes sense. Basically, you have a specialized cone that moves fast. We shove some plastic pellets in that bad boy, and it creates whatever 3D image, not 3D image, 3D printer piece. So like if you want to make a coffee cup, it makes a coffee cup using that specialized cone and those plastic pellets using heat.
Right. So, I mean, a easier way to visualize it would be if you remove that screw from it, and you think of like when a chef is putting frosting onto a cake. If that chef was like Eddie Hall, and that little plastic bag was made out of something extremely hard, and the pellets were large enough to where they didn't fit out the end of that frosting bag, he could just sit there and squeeze it until there was enough energy built up inside the system from friction to melt the plastic, and then it would start coming out the end. And then what the printer that you see, like most people see the thing whooshing around and hear the voo, voo, voo as all the belts are going. That's the 3-axis system I was talking about earlier, moving that essentially pencil around to draw whatever you're trying to print. So it doesn't all come out at one time. It's all just being deposited on top of each other. Like one line of filaments being deposited on top of itself to create the wall of whatever piece you're printing.
So Caleb, this is why 3D printing a better manufacturing method than the traditional method? Can you elaborate on that?
So it's not necessarily always a better manufacturing process. The big advantage of 3D printing is that you don't need to add any additional tooling. So you don't have to go get a die made where you like traditional plastic injection molding. You need to have a die for each piece that you're going to make, and those are expensive because they're made out of metal and they need to be reusable and all that. But 3D printers can also, on top of that, if you imagine a die is made out of two pieces that are pressed together. So if you have some really complex geometry, like a hook, for example, or a bunch of hooks in a bunch of that are all facing different directions, you might not be able to pull those two pieces of the die apart once you've poured the material into it. So a 3D printer would allow you to create that complex geometry without the added hassle of making an extremely complicated die system in order to forge the same, or in order to pour the same part.
Okay, so what types of manufacturing besides a cup would 3D printing be better than the traditional?
So there's a lot of aerospace applications. There's a lot of prototyping applications. So it increases the speed at which you're able to prototype, because you don't have to wait for a machine shop to get stuff back to you. You can 3D print stuff in metal. You can use like sintering processes where it's almost as strong as a part that you would have forged. So you can actually put 3D printed parts into real high strength applications, like in an airplane supporting supporting some kind of load for the wing, and that kind of stuff. So if you have like extremely complicated geometries that are crucial, and lightweight is also a big deal with metal stuff, because then you don't have a bunch of extra fillers in areas where you just weren't able to get it out of the die. I also, there's a lot of like, if you think about like a process where you're removing material instead of adding material, like a die, you're adding material into the die. If you're removing material, you start with a giant piece of metal and then you start machining it. So that's what I do, is I make the cutting tools that machine that metal. But you're losing a lot of material sometimes, depending on the shape of the rough material you're working with. So then you can go scrap that and everything. But a lot of the time, if you're doing it in like kind of a small production volume, it might make more sense to 3D print it, so you don't have all of that extra material that you're basically just throwing away.
Okay. So getting back to your business, so can you just give us a, not in like in detail about the company, kind of give us like the business journey of when did you start it? Who did you start it with? Was it profitable? Was it not? Is it still ongoing? Kind of give us the business aspect, not more the technological aspect.
Yeah. So business wise, we were kind of disorganized because we didn't even really know what we were going to do with the technology. The way that the company actually started out, we were going to try to make 3D printers for educational applications. And one of the guy that I co-founded the company with, his name's Jacob Bonowitz. He is a software engineer. So we were working on designing a web application that would interact with the 3D printer. And it would teach high school students how to do very low level engineering tasks, because they don't learn anything about that kind of stuff in high school. And there's not really a way for them to know if they are going to enjoy mechanical design or an engineering discipline if they don't get to try that stuff. I know they don't have like the calculus resources to be able to do a lot of the calculations, but they should be able to kind of intuit a lot of it. So that's what we were trying to do. But then we learned that it's really difficult to break into the educational sector, because you have to get the support of the school systems, and they have to approve the purchase of whatever it is you're trying to sell. And it's very, very difficult to get them to say that anything is useful. So we ended up pivoting by way of that National Science Foundation I-Core course. What they do is they teach you how to, oh, and by the way, I should add also, we had a big team of people that were all also on the lacrosse team, were engineers that were working on stuff. Specifically, there was a guy named Thomas Miles who was doing a lot that was very, very helpful on the mechanical design stuff. But there was a point in that program where you're going out and talking to a bunch of prospective clients, and they teach you how to ask people questions in a way where they don't know what answer you want them to give you, so that they don't give you biased opinions, and you can figure out if that person is actually going to buy the product you're trying to supply or not. So when we went out and we did those interviews, we figured out that the school teachers and the school systems didn't even want our product, but that there was a different market, which was in the automotive industry, that did want our product. And we kind of figured that out just by connecting dots with random people that we were interacting with throughout the course of those interviews.
So you basically pivot away from education because you know that's extremely hard to get into. Are you currently working with automotive companies, or is that a little hush hush?
No, we're not working with anybody right now. We're working on, we're actually late. We were supposed to get our first prototype samples out to some of our partners who are designers. We partnered with with a couple of people who design the parts that we're manufacturing of their own volition. And so what we're doing is we're providing them a platform to be able to sell the parts that they design. Because right now they just post pictures of them on Instagram as renderings, and they never do anything with them. But we were able to figure out that there's this giant unused surplus of designs. And the only reason that they're unused is because there's no way to make them, because nobody's going to go out and get the expensive tooling made, the dies or whatever else, to manufacture them or make them out of carbon fiber or something. So we decided that we were going to have a shot at 3D printing it. And I think in the next probably about 3-4 weeks, we're going to have some feedback from our partners who are designers on the build quality of the parts. And we're hoping to release our first product for sale in like the next 6 months.
Oh, that's awesome.
Thank you.
Nick, do you have anything to add? Any questions for Caleb?
No, this is pretty crazy. Whole new world out there on the 3D printing side of the world. No, I'm just trying to soak it all in.
There's a lot of experimenting that goes on right now in the 3D printing world. There's a lot of super interesting stuff, and I mean, I'll tell you, even I fully support the business model that we're pursuing right now. But over the course of the time that I've been working on this, I have developed like a whole list of ideas that 3D printing can be used with. Something that's really interesting to people who don't even necessarily have a clue what's going on in the manufacturing world is a concept called compliant mechanisms. There's a guy, he's alive still, so it's a relatively new thing, but he wrote a whole textbook on how to design a system, like a working, like for example, a switch is a system. It historically has been a system of multiple components that work together to make it so that there's an on and an off stage. This guy figured out how to take a single piece of material and design it for infinite life so that it can bend or have hinge points inside the material. So it's one piece, most of the time 3D printed, but it can bend and have multiple states. So like a switch has the on and the off state. So he was able to the first thing I think he made was a vice grip where the whole thing was 3D printed, but it still was able to exert the same amount of force as a normal vice grip in between the claws on the end because of the way that he designed the levers. And it actually uses just a small, like the hinge is just a thinner piece of plastic connecting the levers. And it's designed so that when you bend it's not going to reach the point of yielding and cause a failure of the mechanism. So most of the research he did is based on figuring out the math of like how to decide when the material is going to fail. But he designed stuff like he designed a switch. Veritasium did a video on it called Why Machines That Bend Are Better. That's a really good video. But in that, he talks about how he designed a nuclear safety switch. So it's just a little tiny, it's so small you can't even see it, but it blocks a hole that a laser will shoot through to charge the nuclear system. And it obviously, in a nuclear application, you can't have that switch fail. So the best way to do that was to use a compliant mechanism because there's no moving parts other than the single piece. And that was one of the first like industrial applications that he talked about that he was able to use a 3D printed part in a military application.
And that's kind of what so the 3D printing gig is your side hustle. And you said you do work for some Department of Defense companies and you do mostly aerospace stuff. Is that what you're talking about?
So, well, like right now I work in just manufacturing. We do stuff for automotive companies. We do some stuff for some of the large defense contractors. And we also do like one-off tools for small manufacturers in our local area too. But in the past, like when I worked at MTI, we were doing a lot of defense. It was pretty much exclusively defense applications. So that was like electric motors for airplanes and missiles, that kind of stuff.
War is good.
War is good.
So Caleb, Nick, do you have anything more to add? Because if you don't, Caleb, give a shout out to your socials.
No, this is amazing. I don't know anything about engineering, so
that's all right.
The only thing Nick knows about a switch is a light switch.
What about a fully automatic weapon? That's a switch too, isn't it?
True.
Yeah.
Depends if you're on O block.
Yeah.
Shout out O block.
So Caleb, where can the people find you?
Best place to find me is on LinkedIn. My name's just Caleb Nolen. Nolen is spelled Nolen. Caleb is spelled Caleb. I also have a Medium profile where I blog. I just posted my first blog about a week ago. But I'm going to be on there a lot more often. I don't use social media other than that, though.
We'll shout out the
blog.
Put
all stuff, down below.
Sweet.
Nick, where can the people find you?
I'm Nicholas Calling on Twitter, Instagram, and Facebook.
And can you please, if you're listening on Spotify, go to the YouTube, like and subscribe, like and subscribe, like and subscribe. It's
Smash that like button.
Smash that like button. It's PT_podcast. And then follow the Instagram. It's real_PTA_podcast. And I'm your host, John Caligiuri. Thank you so much for listening. God bless and have a good night.